Well, welcome everybody to another EOL seminar. It's my pleasure to introduce today's speaker, John Lehman. He's a physicist and leader of the Sources and Detectors group at the National Institute of Standards and Technology, known to its friends as NIST. His group provides laser power and energy calibration services worldwide, and they also perform related metrology R&D. He's been traceable at NIST for more than 30 years, and in recent years, he became a fellow of the Alexander von Humboldt Foundation in Germany. That's very prestigious. And there, his pursuits included a study of sparkle.
Where'd you get that?
Today,
I can explain.
That's his choice. Today, John's going to tell us about his group's development of chip-scale absolute radiometers.
All right, thank you. I could explain sparkle later. But you must have gotten that from the internet. Okay, thank you. Thanks for coming, everyone. Let's see. I think I'm just going to dive in. No further ado. So I am from NIST in Boulder, and I'm glad I brought this slide today because that's not obvious to everyone. I am from NIST, but from NIST here in Boulder. And many of you know, or maybe are more familiar with the campus in Gaithersburg. And we are the Sources and Detectors group. There's 6 people from our group here today, so we have a good showing. And I'm in the awkward position of presenting their work, so I hope that I don't embarrass myself or misrepresent what we are doing. And so any of you who I met today or others who find interest in what I'm talking about, you're welcome to visit us. We're just over up against the foothills. You know where NIST is here in town, so please visit. Okay, so I want to thank the people who have done a lot of this work, and I want to point out that a lot of this work is done in collaboration with LASP. So the folks you see here, Michelle, Nathan, Chris, Yvonne, Malcolm, Thomas Garris. Thomas is not here with us today, but actually the people from NIST are here today. And then from LASP, we work with Dave Harbour, Eric Richard, Greg Kopp, Ginger Drake, and some other people. And then we have a couple of guest researchers who have been involved with this work. Julian Grobner, who's here also today, and Zeus Gutierrez is from the Mexican National Metrology Institute, and Julian's from the PMOD in Davos. Okay, thanks, you guys. Here is my brief outline. I'm going to present to you a broader context of NIST, just so you're more familiar with what we're doing and the idea of standards and traceability, and talk more in detail about measuring optical power, and I think that'll be useful after our discussions this morning. And then, the rest of it is just going to sort of be speed dating. I have lots of pictures, very low on substance, high on hopefully in just ideas and things that might lead to discussions later. If you see something you like or might prompt further discussion, let's proceed with that. Okay, now I'm going to talk about NIST stuff first. So I use this, the people here from NIST have seen this before. I use this in a lot of my presentations just to introduce where we're coming from. So our group is Sources and Detectors group, and we are responsible for calibrating laser power and energy meters. That's sort of our bread and butter for NIST. And we do this over nearly 23 orders of magnitude in terms of photons per second. And so this is a plot of, okay, I have this fancy new laser pointer thing. It's not actually a laser pointer, so prepare to have your mind blown. Watch this. Here it goes. Come on. It's not working. Now my mind is really blown. It just worked. You saw it work. Oh, I'm pressing the wrong button. Okay, here. So this is power and energy as a function of wavelength. So we calibrate things from the UV to the far infrared, 400 microns, and from single photons all the way to 100 kilowatts. And we serve these industries, everything from quantum communications all the way to miscellaneous military applications. We do a lot of work in industrial manufacturing for laser power and energy measurements for laser-based manufacturing. So what I'm talking about today is more, I guess, related to space-based sensors and some of our core areas related to communications. So I always say that our research should be driven by the calibration services we provide. That gives us a waypoint. So this is another way to look at that same plot. In terms of our growth areas, we're headed towards higher powers, very low powers, and longer wavelengths. But there's also this, what I call squishy middle, where we want to be faster, cheaper, better if possible, but it's not necessarily pushing the boundaries of power or wavelength and so on. So that's my way of saying we serve a broad group of commerce and defense with not that many people, and it's also challenging just from a technological standpoint. So I have a few slides that I hope capture that idea, because this is a laser, and that's a laser, and that is not a laser. And the point I'm trying to make is that laser measurements, laser power, lasers are not a commodity, unlike, say, a voltmeter or a clock or something like that. There's many different types of lasers, different powers, different wavelengths, and so on. And there are no standard sources in laser power measurements or optical power measurements for that matter. So we have to sort of guide our research to have the most impact with limited resources as a result of that. Okay, so that's sort of a big picture thing about our group. This is a little cartoon that describes the present realization of optical power. That is the method by which we realize optical power. As I said, there are no standard sources for optical power. There are standard detectors. And this little cartoon shows the essential elements of a primary standard. So typically what we're trying to do is measure optical power. So we absorb as much of the optical power as possible on some sort of platform, and then substitute some amount of heat electrically to elevate the temperature of that platform an amount equal to the optical power we're trying to measure. So we call this method electrical substitution. And in order to do that accurately and quickly and so on, we also need a weak thermal link to the world and some reference temperature. So our present realization of optical power is really through electrical measurements and the volt and the ohm. Okay, so this is what we're stuck with if we're going to think about measuring optical power for whatever application. Okay, so this is a picture of what the primary standard looks like in the world for the most part. Like most NMIs in the world have a cryogenic radiometer that looks like this, and it has these essential elements I just described: a heater, an absorber, typically a cavity, which is massive and relatively large, a thermometer, and some weak thermal link to the world. So the dollar is here just to give you a sense of scale. That's about how big this thing is. It actually sits in a liquid-cooled cryostat, a helium-cooled cryostat, very large. With electronics, something like that probably costs $750,000, maybe $500,000. And this technology was established, I think, at NPL in the mid-'80s, for the most part, as the primary standard. But the idea, the concepts of electrical substitution were sort of established in the late 1800s at PTB in Germany, at that time PTR, by Ferdinand Kurlbaum. And he did this, he used an instrument like this to establish things like Planck's constant and what we know as the black body, or the fourth power law, I guess. There's some informal ways of stating that. But so this has been around a long time, and the technology we use today at these low powers is still the same. Okay, and so Nathan Tomlin, who's in this room, like almost 8 or 9 years ago, we started doing things with carbon nanotubes, vertically aligned carbon nanotubes, and we had this idea that we could capture everything in this radiometer in just a chip. Okay, so I'm sort of jumping ahead of myself now, but you'll catch up, I'm sure. But the idea was we could put carbon nanotubes on a little chip, and the nanotubes, because they're black and they have good thermal conductivity, we could do it all in a single chip, and it would be faster, cheaper, etc. And at that time, we had this idea that the absorber, the thermometer, and the heater could all be the same thing. And luckily, we didn't know any better at that time because it took a long time to go from there to where we are now. And we've learned a lot along the way. Even though this device looks pretty cool that we were able to make, there's a lot more of engineering that's gone into it since then. So Jump ahead about 5 years or so or more, and we got a little better at doing this. This is a complete planar, what we call a planar bolometric radiometer, and it has all the essential elements that I described for the detector part, and that's shown here. But there's also some more complications in this reference block that's part of the overall radiometer that we had to wrestle with. So this is just sort of a tease that, okay, so we're going to use carbon nanotubes. We can do some micromachining in our fabrication facility and replace this whole cryogenic radiometer thing with a single chip. That's the idea. But it became a lot more complicated than that. So what I'm here to talk about today is the idea that we have a whole bunch of skills that we've developed, and since Nathan came along, we now have Michelle Stevens is with us, Malcolm White's with us, Chris Young's with us, Yvonne's with us, Julian's with us, and we have this, we're able to pull together all these resources to make very accurate radiometers based on chip scale design that hopefully will replace these older legacy primary standards. So along with the chip design, we've learned to do the integration for this. In this case, this is a mechanically cooled system, refrigerator, not liquid helium cooled. The characterization of these nanotube materials and the low temperature behavior and so on. And then the really nitty gritty where we document our uncertainties to 2 or 3 decimal places, the documentation and so on. So we have this whole thing in our portfolio now with some very skilled people, which gives us the opportunity to hopefully make contribution in different areas. So one of the big pieces of replacing the radiometer that I showed you is the cryoengineering, where we're replacing a liquid-cooled cryostat with a mechanically cooled system. So this is an example of, very quickly going from sort of the schematic idea of the essential components of the radiometer system to actually implementing it into a multi-stage temperature control system into commercially available refrigerators, which you see here. So we now have 4 cryostations underway with the Air Force and some other National Metrology Institutes. And I still haven't done this all completely justice. I'm sort of leading you into everything I want to talk about. So all of these things have gone into making complete systems. And one of the things that's important going from these liquid-cooled systems to mechanically cooled systems is the fact that we can do very stable low-temperature operations. So this is just a plot from Malcolm showing the resistance noise and temperature noise as a function of frequency. Bottom line is that we're able to achieve like 2 microkelvin peak-to-peak stability in a mechanically cooled system, which 5 years ago we couldn't do. I don't think anyone else could do. But that allows us to compete with these systems that are 35 years older more. Okay, so in another thing we discovered along the way with our nanotube development, mostly by accident and somewhat unfortunately, is that some of our wiring that we exposed to the nanotube growth process became superconducting at temperatures we did not expect. But since then, we've learned to exploit that. So now this chip, which I showed you before, has thermometers that are actually based on superconducting transition edge sensors. So we've incorporated that into the fab process and the materials development so that we have a chip scale radiometer with superconducting transition edge thermometers. And there's this is a whole nother can of worms, and I could go into that, but that's part of some of the lessons we've learned over these last several years. So here is just an example of the behavior of some of these thermometers that we've developed for these cryogenic systems for measuring absolute power. We have a niobium TES shown here, and then the vanadium is actually not a thermometer, but some of our wiring in the leg of this system, the weak link, showing these elevated transition temperatures. So as I said, this is another thing that's sort of a whole other can of worms, but I want to introduce you to that to give you some idea of the development, the cryoengineering, and so on that's gone into this. So here's a final thing that we've actually built and documented, and it is a calibration standard at NIST now. This is a fiber-coupled radiometer, and it has all the essential elements of an absolute radiometer that I described to you with a nanotube planar planar bolometric radiometers packaged in a two-stage temperature control system with fiber coupling and so on and so forth. So it's like, this is done. We've drawn a line under it. And we also have a free space system for just what the name implies, for free space optical radiation measurements. So these sort of represent our lowest uncertainty measurement systems, representing absolute standards. And this particular system that you see here is headed for FTIR-based measurements in the infrared. Okay, now I'll talk about, I just wanted to bring that up to give you some appreciation for how deep we're willing to go, right? Or how the extent to which we are developing these systems. It's not just, oh, we did something cool with nanotubes. We're actually making high accuracy calibration systems. And I'm going to talk about our space applications, the work we're doing with LASP. And we sort of, in tongue-in-cheek, we call this NIST on a spaceship, because we also have a program called NIST on a chip. Okay, so some of you may be familiar with CubeSats. I stole this picture from the Canadian Space Agency because it says it all. So if you're not familiar with this, a CubeSat is a very small satellite with a form factor of about 10 centimeters on a side, a little bit bigger than a Rubik's Cube. And these can be stacked up to 16 units to make a small satellite that can be chucked out of a rocket on some other payload or whatever. And the point is, these are cheaper, smaller, consume less energy. They can jump on other payloads and other missions, and typically their mission is short-lived. And so our role with LASP was to develop the instrumentation that goes into some of the components of this CubeSat, right? So it has these other properties, but our application is, for scientific research, but we're sort of anchoring the measurement uncertainties and the absolute accuracy of the measurements in this sort of thing. So we're talking about CubeSat missions. So we came on board with LASP because they have two missions that are now on the space station. There's the Total Irradiance Monitor and the Spectral Irradiance Monitor. So these things are pretty massive, right? They're about yay big, I think. And right now, they actually are not satellites, but bolted on the space station. And our goal, well, LASP's goal, and our job to participate with them is to reduce these things to 6U CubeSat format. And our role in that is to put the measurement instrument inside. So to make very small radiometers for the absolute radiometry in these two types of missions. So the first one for the spectral irradiance is shown here. This is just so we have the ability now to what I would call we've mastered this CMOS-like nanotube growth along with microfabrication of silicon to make an absolute radiometer with all the essential components that I introduced to you. So this thing is a complete radiometer having these dimensions with an absorber, a heater, a weak link in the form of this silicon nitride, and a thermometer which is bonded onto that substrate. So that's a spectral irradiance detector, and then this is part of some other electronics we've developed, or mostly LASP has developed as part of this instrument. So this detector that I showed you is actually part of a pair of detectors, which sits behind two slits, which sits in a spectrometer, which goes into a CubeSat, which will replace this larger instrument, which I just described. So that will go and this is in a 6U CubeSat, and this is supposed to be launched in this year. Maybe not June anymore. Maybe it's more like August now. But it's been vibe tested. It's so far so good. It's working, and so this will be our first NIST on a chip actually in space, and sort of taking our nanotube curiosity all the way to a finished instrument, a scientific instrument. Another space mission we're collaborating with LASP on is for total irradiance. So this is a picture of the latest, well, not the latest embodiment of this instrument, but it looks sort of like this. There are 4 1-inch diameter absorbers that are just staring at the sun and measuring total irradiance. And there's also some retroreflectors that are added to this, and they go in this egg crate type design. And this will replace this total irradiance system that I showed you. And the goal of this is world-class. The uncertainty goal is 0.1% in space, which is very ambitious. This is supposed to be at least a 2-year mission. So now I'm going to give you some other applications. I'm going to start showing, you're going to have less content and more pretty pictures. So this is a larger version of the planar bolometric radiometer. When I was putting these slides together, I decided to call it the extra large planar bolometric radiometer, so the LPBR. And this has a 1-inch absorber, and it has all the essential elements that I introduced to you before: a weak link, thermometer, and a heater around the perimeter with electronics that were incorporated and built by Yvonne. And this is for an Air Force project as well as our own NIST internally funded work for a new primary standard for measuring laser power. And then we've also, Chris and Nathan have recently managed to make a thermopile that is compatible with nanotube growth. So you could think of this as a high temperature thermopile array or a bunch of junctions that we can put nanotubes on. So this gives us options to think about pyranometers, and other sorts of technology, at least even just pyranometers staring at the sun or other applications. So that's, I would call that emerging technology. And then we also have a project that just started this year with NASA that is an array of planar bolometric radiometers. So our goal is to make a 32-element linear array with electronics, with each pixel having all the essential elements that I introduced to you. So it'll have an absorber, it will have a silicon nitride membrane perhaps, this is all very early stages, some sort of weak thermal link, a thermistor, and a heater. So along with the electronics, and then there's one other dimension to this where the reference voltage for this device is tied to a GPS receiver, so the voltage calibration is tied to a quartz oscillator, which is synced to a GPS signal. So that gives us some sort of remote assurance about the voltage calibration to which that is traceable, ultimately, as I described, for the primary realization of the optical power. So we just started that this year with LASP, and it's a 3-year project, and so we're really excited. It's going to be very challenging, though. This is extremely difficult. So I know I'm looking forward to it. I'm not sure everyone is, but it's going to be great. So we also, since as long as I've worked at NIST, been building pyroelectric detectors for various applications. So this is a plot of the reflectance of a commercially available carbon nanotube coating on a pyroelectric detector that we make, a 1-centimeter pyroelectric. This is total hemispherical reflectance as a function of wavelength. So this goes out to 11 microns. And so this noise and spectral character, it looks kind of dramatic, but really we're talking about 0.1% variation in spectral uniformity, which is quite good for a device like this. I don't know of any available commercially. And this is an example of the spectral responsivity of that detector. And to my knowledge, there's only one place in the world where you can get spectral responsivity out to 24 microns, and that's at the National Physical Laboratory in the UK. And so this is the spectral responsivity of these guys. And if you've ever worked in this area, there's really nothing like these detectors. And we have sold over the last 30 years like 80 of these to various laboratories for primary standards and so on. So the nanotube coating on these is actually a bit of a breakthrough, and it makes it a little bit more of a commodity that we're interested in using in all sorts of applications. Another thing, this is sort of a shameless advertisement, at the very low end of the power range, we also have the ability to do single-photon detector calibrations. So I can't imagine putting this on a satellite, but I could imagine maybe putting it on an airplane. I don't know what the application would be, but just for completeness, we have developed a completely portable / shippable single-photon calibration system. It's the only one in the world that I know of. And it's part of an international comparison. So it travels the world without an adult supervising. It actually just goes with a manual, and that can be used. And that's a part of a NIST calibration service. Okay, so now I'm going to go back to where I probably should have started. I'm going to go back to the beginning, in a sense, and talk about carbon nanotubes. And so a lot of what I've talked about is all started with this premise that the advantages of carbon nanotubes and micromachining silicon might give us the opportunity to replace these more massive cavity-based radiometers that are built, I would say, from the top down. So we have, with the chip and the microfab capability, we can start from the bottom up and make, dozens of chips on a single wafer and so on. And the nanotubes are important. Okay, so a single wall, so I'm going to talk about nanotubes now. Okay, a single wall carbon nanotube conceptually is a sheet of graphene rolled up into a cylinder with half a buckyball on each end. So that's conceptually. It's not actually made that way. And these things are a couple nanometers in diameter, and they were first observed in 93 while looking for multi-wall carbon nanotubes, which were found looking for buckyballs, I believe. So single-wall carbon nanotubes, if you were to look at them, just hold them in your hand, they would look black, but they're typically not actually spectrally uniform. Multi-wall carbon nanotubes, however, are inherently very spectrally uniform. So this is an SEM of the side view of a forest of carbon nanotubes, right? And these are made up of concentric cylinders of single-wall carbon nanotubes. And the aspect ratio of these things is incredible, right? So if you could, so we have grown more, a little straighter nanotubes than this. But if you want an idea of the aspect ratio of this, you can imagine a telephone pole about this big in diameter, 3 miles long, right? And these stand up together. So what that gives us is a very low density, spectrally uniform material to use as an absorber. And the low density is important because there are many things you could make to be very black just because the photons will bounce around if they have sufficiently low density. So there's a combination of the intrinsic properties of the graphene or the graphite from which these are made as well as the density. So what we're looking for in this carbon nanotube coating are three essential things. The index is very nearly 1 typically because we have this sort of vague boundary between the air and the nanotube forest, if you want to call it that. And because of the low density, and I should say maybe change the order of this and say the thermal diffusivity is very large because the thermal conductivity along the tube axis is very large, along the sort of the graphene planes. And the specific heat is just so-so. But with this kind of thermal conductivity and density, we can get very large thermal diffusivity, which means we can make something sufficiently thick to absorb a broad range of wavelengths and still have it be a good absorber that doesn't add a lot of thermal mass to the detector. So this is the magic of carbon nanotubes. There's nothing else like this. Nothing as spectrally uniform, nothing with that kind of thermal conductivity. And that's what we've sort of banked the last 10 years of our research on, is making use of this. Going beyond the sort of the novelty of the research journals to doing something with great impact. So this is a plot that I've had for several years, but it also gives you a great idea of the spectral uniformity of carbon nanotubes. So this is a plot of directional reflectance as a function of wave number or wavelength from the visible all the way to 500, well, near infrared to 500 microns. So the reflectance is less than 1% all the way to about 300 microns, which is quite remarkable. So the detectors I've shown you so far, in principle, if it works at 1 micron, it works just as well at 200 microns. And so that opens a lot of doors in terms of the spectral range that we can work with in these detectors. And not only are they uniform and black, they're really black. So this is some characterization that we did with LASP of the nanotube forest that we've grown here in Boulder. So there's 3 SEM images here. There's some as-grown nanotubes. So we're looking at a plan view. We're looking end-on the nanotubes. And we've done some post-processing with oxygen plasma treatment to change that morphology and change the density a bit. So there's two types of plasma treatment to try to improve the spectral nature of these materials. And so what I have next is a plot then of the total hemispherical reflectance as a function of wavelength for these three materials. So it's possible, bottom line is, it's possible for us to achieve reflectances less than 100 ppm. So that is evidence that there's really nothing like this. I mean, there are cavities that aren't this black. So that's a great result that we rely on, or that sort of result is what we rely on to have confidence that it's worth pursuing. And with our collaboration with LASP, we've done lots of evaluation of these carbon nanotube materials. They have a laser-based reflectance system that will actually do uniformity measurements of reflectance. And we've duplicated this, at least without doing the spatial uniformity, at our labs in Boulder. And with this system, we can plot spatial uniformity of the reflectance. So this is an example of some measurements showing very low reflectances over 5 millimeter areas or larger. That, again, there's really nothing like this. And that sort of characterization is part of the very thorough documentation and so on to make these valid radiometers. Okay, so that's about all I have. I will just go through some things. So I introduced this idea that the primary standard for optical power is this. And our goal is to move away from this. This is over 35 years old. We want to go to planar bolometric type radiometers using microfab and carbon nanotubes. And along the way, we've learned a lot. We've learned about some superconducting materials, sort of multifunctional operation of these chips that have thermistors, heaters, absorber, all in one wafer operation. And we've gone on to demonstrate that this is good enough to put in space. So we have at least a solar irradiance or spectral irradiance detector going to space this year. We have part of our bread and butter is just making pyroelectrics that are black and uniform. And the future looks like this, where we're going to make an array of planar bolometric radiometers to start thinking about linear arrays, 2D arrays, and so on, with some added features for better accuracy, long-term stability, and so on. So I think that's all I have. So that's it. Thank you. Do you have any questions? Questions? I've talked to you already, some of you already, but if you have questions, please.
Thank you, John, for a really fascinating talk. Questions?
Anybody? Yes?
I'm wondering how the response time of these smaller devices compares to the old legacy one, and what is the response time of your new devices?
So since they're here, so Malcolm can jump in here and correct me if I'm wrong, but this sort of device has a time constant in the order of seconds, 5 seconds. Whereas these, for FTIR, we're looking at milliseconds. So 100 times better, 10 or 100 times better. And that's crucial for things like FTIR, and I'm sure for the imaging as well. So, yep. But we can engineer that to some extent. That's part of what we pitch. If we can control the features or the dimensions of this weak thermal link, we can control things like the speed and sensitivity and so on by that thermal engineering. So, because we don't entirely ignore the nanotubes as part of the thermal equation, but it's basically we get the absorber for free. So it's really about engineering the properties of the silicon structure or silicon nitride structure. So, would you agree? Sort of. Yeah. Anything else? Yes.
Sort of along the same lines, if you're thinking about using these as the carbon nanotubes as a reference black body, to have very high emissivity, does your answer to the previous question imply that you could modulate that temperature at a near kilohertz, 100 hertz type rates?
I suppose it does if you think about making the structure in a similar way. I mean, when I think about making a black body, I would think of just making a big flat disk, which would not necessarily have the same response. But I know of occasions where people have heated or modulated the heating by a laser, let's say, on the backside, which might, so you could suspend the, quote, black body and heat it rapidly. So I think it's more a function of the mechanical coupling to the world that would determine the speed of the black body. So in principle, yes, we could make it faster, but I haven't really thought that through. But it seems like you could. So that's a good question.
I noticed a lot of the plots kind of tapered off in the fractions of micron range. So what happens down, below 200 nanometers? Do they?
I don't know. There aren't really any measurements around that I know of below that wavelength range. I know that. So if you look in the literature at just nanotube optical properties, you see actually an increase because there's a plasmon resonance at about 255 nanometers. And then after that, the roll-off below 255 is quite precipitous. The roll-off meaning decreased reflectance is quite dramatic. So I don't know how low it'll go. I mean, we don't have the resources to do those measurements, and most of the published information relies on a commercial spectrophotometer that stops around 250. So does anybody else know below 250, really? In principle, it should get lower reflectance. Once you make it past that plasmon resonance, it should get better. So usually it's easier to absorb things in the UV, so I would hope.
And they're not susceptible to damage from intense radiation? Or they are?
Yeah. So there are different levels of damage. So probably the most risky for our space stuff is atomic oxygen will attack carbon nanotubes. Ozone will attack carbon nanotubes. I'm told or assured that for these space missions where we're not actually looking in the direction of travel, the risk of atomic oxygen and other sorts of damage is minimal for, say, a two-year mission. And we have lots of research and information about the effect of humidity and hydrophobicity and things like that will affect the topology and increase or decrease the reflectance. But for the most part, we have confidence that, short of actually jabbing and damaging the material, it should stand up to these sorts of tasks that we're trying to work on. So that was kind of a hand-wavy, but damage is kind of a hand-wavy thing, right? We hope. Anybody?
Any more questions? Well, if not, let's thank John again.
Thank you.